All right, I'm going to assume it does. So thank you for this opportunity to speak with you today. So this is work that is done by a group. I'm just up here representing it, and it's going to be on observational assimilation application. And so this is rather different than the talks that I've given for the past perhaps 5 to 8 years, in the sense that it doesn't have anything to do with climate modeling. What it does have to do with is this APAR project. And the APAR project is an airborne phased array radar. This is an effort that's a collaboration between NCAR and NOAA. And they're building the instrument now. And so what it will be is it will be a Doppler radar, 4 panels that are mounted on a C-130 aircraft. And then the aircraft will be flown through extreme weather. You can see in the lower left panel a diagram of the aircraft and also the radar beams that it's emitting. And and this is to replace a retired Eldora aircraft that had this capability. So some of the science drivers is hurricanes, extreme precipitation events, Arctic studies, cloud aerosols, and radiation studies. So so this data is obviously collected on the plane, and then a variational analysis is performed on it. And this is using this blind analysis at metascale using radar and aircraft instrumentation, or SAMURAI for short. This is developed by a professor of Michael Bell at CSU. It consumes these airborne observations, and it generates a variational analysis of several variables: wind, precipitation, vorticity, et cetera. And so then this analysis could be used to drive numerical weather prediction models. It's a C++ code with OpenMP based parallelism, so it's a single node application. So there's a couple of examples of the analysis in visual form. If you look at the one on the right, you can see what appears to be a hurricane, and you can see the little black airplane that is flying through the hurricane. And so that's so basically, you know, the airplanes go out, they fly through these weather phenomenons, and then the SAMURAI will calculate what exactly it flew through. So some of the outline of the talk, you know, describe some of the background and motivations for the work. We're going to move on to the initial state of the code. This was a SAMURAI. The SAMURAI optimization effort was funded by the Earth Observing Laboratory through a NOAA grant, and they came to us because the processing was taking 2 to 3 days to perform an analysis, and this was again using a single node, and for test data sets that were moderate in size, not really what the instrument was going to generate. It should be noted that the APAR instrument doesn't exist yet. It's in the process of being built. I don't know the exact timeline, but we're probably a couple of years off before we actually have flight data. You know, the things that were taking 2 to 3 days, the APAR data is going to be about 16 times larger. So that looks like months of processing time. And so really they came to us and asked us, what can we do to accelerate the processing of these observations? And really the goal at the start of the project was that they wanted to be able to run the analysis in less than 6 hours. So to put it into the NCAR computing environment, they have 6-hour time windows for scheduling jobs. So some of the challenges of this code, the code, I have to admit, was kind of rough. It required like GUI C++ library for string manipulation. And it was, the execution really was only possible in a Docker container because it used a bunch of old versions of code. So the Docker container would not run on the NCAR supercomputing environment due to security restrictions. And one of the other challenges is that our performance analysis tools did run in on supercomputing systems. And so the application and the performance analysis tools were incompatible, at least initially. It had very long run times, 2 to 3 days. Is prevented execution again in the queuing system, and so it was only possible to initially to run this code on a laptop or cloud provider. And some of the larger problems exceeded the memory of a typical laptop. So it's kind of a challenge to challenging nut to crack to begin with. So our plan of attack was we would port the Docker container to a Charlie Cloud, and the Charlie Cloud is a container that is actually allowed to run on the NCAR computing environment. And then after we had the Charlie Cloud version, we could port it to a standard HPC cluster, analyze the performance of Samurai, optimize the code. And then we wanted to, I was suspicious of the conjugate gradient solver that they were using. And we wanted to see if the use of the GPU was possible for this program, for this application. All right, so the initial port to the HPC cluster. So, the original code was a binary executable in a Docker container. It made development nearly impossible. I remember, yeah, so one of the things that we initially did was remove the Qt library dependency and used some modern C++ features, redesign the CMake build structure so that it could support different compilers, and also performance analysis tools. And this actually was the biggest effort in the whole project, was to kind of pull this out and allow the code to be worked on by multiple team members. So moving on to the code optimization. So a little bit about the computational characteristics. It's a matrix-free solver, and it's implemented by several operators that I'll describe, and then have different kind of performance characteristics. So so the main data structures is there was like a 3-dimensional physical grid. And so this could be thought of, you're taking all these observations of rays that are coming out of these Doppler emitters, and you're kind of interpolating to, or assimilating to figure out what kind of hurricane did I just fly through. It has these observational matrix H. So, and this could be quite large. It's so this could be 32 gigabytes or larger. So so that presents some challenges. So some of the computational routines, there was the solver routines, either it was CG or later a Newton CG solver. Excuse me. There was pencil calculations on the physical grid. So you would collect a pencil of data that was contiguous in, excuse me, either the X, Y, or Z dimension, and perform an operation on it. There was the multiply by the observation matrix, and also the multiply by the H transpose matrix. So some of the performance issues that we identified, excuse me, was there was inefficient indexing and limited thread parallelism over the physical grid. In several of the subroutines, there was limited thread parallelism with the H transpose operator. There was non-unit stride issues for observational vectors, numerically inefficient conjugate gradient solver, and no threading within the existing CG solver. So That's going to be a whole nother section of the talk when we talk about solvers, but I'm going to describe next kind of some of the things that we did for code optimization. When the code was written, it was a while ago, and there was 7 variables that it performs data assimilation on. And so the loop was over the 7 variables, and so that really is quite limiting for the amount of parallelism that's now on node. So we relocated the OpenMP loop such that it went over the physical dimensions, and so this gave us more parallelism when the calculations on the physical grids and the pencil calculations. So there was, is that really? Okay. There was issues with the H transpose operator called calc H transpose. The original version you'll see there on the left, and so there was a lot of disadvantages to this version. It wasn't threaded. There was indirect addressing on the store, non-stride unit access to the observational vector. So we went about rewriting this several times, and I still don't think we got it right. But the second attempt was to, you see on the right side, and so we were able to thread one of the pieces of this calculation. So it's partially threaded, but there's still indirect addressing for store, non-unit access stride, and excuse me, you know, every time I cough, I feel guilty. The fact that both of the chunks are not threadable is would generate PCIe traffic for the GPU implementation. So there was a third rewrite, and this is what I'm going to present performance results from. And so now it's fully threaded, eliminated the indirect addressing for store, unit access strides, and this is GPU device resident. The downsides of this version is that it has a suboptimal memory data access patterns, and it uses all these indirect, or this lot of memory for address arrays. Excuse me. So I think in the future, we were rewriting it this way because I wanted to avoid storing, explicitly storing H transpose. But I think it's probably a better idea to explicitly store it and then do a standard compressed sparse row format. All right, so let's talk about the experimental configuration. So we were using 2 computational platforms for this work. A node of Cheyenne, which is a Broadwell, and NVIDIA V100. We'll describe the V100 results in a little bit here, not immediately. So 2 different compilers, the Samurai data sets, the physical grids, and the number of observations. So you can think of the physical grid, if you want to run an NWP problem forecast, then that would match your physical grid of the output. So you have supercell and hurricane. The supercell has a larger physical domain, and the hurricane has a smaller physical domain, but it has more observations, and so that plays into the relative costs of pieces of this algorithm. All right, so here's the timing results, and again we have the 4 different sections of code: the SC and SA transform or pencil calculations, and the H transform and calc H transposer matrix vector multiplies. So this was for the supercell, and we were timing to iterate, or 20 iterations to begin with. The configuration on the left is kind of where we started with, and then as we implemented successive optimizations, the OpenMP version 1 was the first version of calc-H transpose plus more threading over the physical, fix some of the index calculations, use the Intel compiler, and then the final version of the H transpose op. So you see we got progressively better speed up, going from 1300 seconds down to 294. So that was a pretty good result. But we weren't really done yet with the optimizations. So we wanted to, next we kind of looked at the numerical solver. And so the big picture here is, we have a cost objective function, and then we want to minimize the Jacobi. So the original solver that was in there was a nonlinear conjugate gradient. And it was using a rather expensive line search algorithm method, so it was Brett's method. And the convergence criteria was also a little suspect in the sense that it was the change in the cost function between consecutive nonlinear CG steps. And so it was kind of hard to do comparison across the gradients for each problem. So so Allison came up with applied a different method, the truncated Newton method. And in this case, we happen to have the Hessian laying around, or I should say we could calculate the Hessian easily. And so that's a good thing. And there was also a cheaper line search line search algorithm that was applied. And we also looked at reducing the relative residual to something that's more standard. And the other thing you'll notice is that we lowered the tolerance slightly to either the -4, and so that was still acceptable, and we worked with the scientists to verify that. All right, so we're going to look at the cost again, except for I added a new result on the right-hand side here. So this is the supercell 10 iterations, or 20 iterations again, excuse me. And now it's dropped down to 44 seconds. And so this was a significant, and the thing that I'm not the thing that I'm not showing you, but I'll tell you, is that the iteration counts were similar, or maybe a little bit lower for the truncated Newton. So getting pretty good speed up here, and but we're not done yet. We wanted to look at also GPU enablement, because the truth was this had huge working set sizes, so large that that some of them actually blew out the GPU high bandwidth memory. So we utilized OpenACC parallel and data movement directives, and we were able to get all the computational demanding calculations to be GPU resident. We're currently using managed memory. There is still a very small amount of host to device memory transfer still exists. According to NVProf, it's 6.3 megabytes versus 108 gigabytes for the high bandwidth to SM. So some of it's still there. It's either a compiler bug or user error, probably the latter. I put my directives in, and then it complains that the device isn't, or the array isn't found. Anyway, something's still going on there. One of the other critical pieces was that we needed to rewrite the calc-H transpose, and that was described previously. So the third iteration was necessary, because otherwise you'd have all this, you'd have this piece of matrix vector multiply that couldn't be on the GPU. So, all right, so what I did here was because I zoomed in because otherwise you can't tell what's going on here. So the supercell case is what we've been looking at before, and it's on the left side. And so now we're comparing the Intel Broadwell 36 core system to a single NVIDIA V100. And you see that we get a nice speed up there going from 44 seconds down to about 15 seconds. And then for the Hurricane case, which has the smaller physical grid and larger number of observations, we dropped from about 40 seconds down to 20 seconds on a single NVIDIA. So so pretty significant speed up when you add them all up together. So this is the question that I asked that maybe I shouldn't have asked, but I'll put it up here anyway, which is how efficient really was the GPU implementation. And so I calculated the roof line and for the various pieces of this algorithm, and it looked kind of pretty bad. So there's as far as expected performance based upon the memory transfer. So you see that we're really doing pretty bad with arithmetic intensity, and by this group that's over here on the lower left-hand side. And I suspect that that's we're just running at the high bandwidth memory rates and or PCIe traffic. So because I mean they're tight groupings, and so you're not getting any cache reuse on the GPU itself. So what does that say? Yes, it's significantly faster than the CPU, and it's probably could be faster, but it is what it is right now. So this is kind of the summary of the Samurai code optimizations. The original case on the Intel Broadwell, it was taking 577 minutes, and the Hurricane was 609 hours. We progressively applied the various optimizations, the initial OpenMP optimizations, the new solver, and finally the new H transpose operator. And so, we draw on a single NVIDIA, we're dropped down to 5.4 minutes or 4.9 minutes on the Hurricane. So we achieved a speed up from the initial version of 106 or 124. And which puts it significantly faster than their target 6-hour window. All right, some future work. I want to improve the efficiency of the GPU implementation, rewrite calc-H transpose again, eliminate all the excessive PCIe traffic, improve memory access patterns on the GPU. The truth is, I could probably geek out about optimizing for the GPU for a while, but I don't know if moving it up to a 500x speed up is really going to change kind of the impact that it had on the science. So iOS serial, so it's now a significant fraction of the time. And we really need a multi-node CPU and a multi-node GPU implementations, because the full resolution APAR data sets are just quite large. Yeah, so just the funding was through a NOAA grant. The team members, I mean, this was a great fun project to work with, because I mean, we were all kind of focused on it, and everybody brought kind of a unique and critical contribution to the project. So I really want to thank my collaborators on that, and also a number of other people, the APAR PI, other people involved in the project, Michael Bell and graduate students, and Michael Dixon at NCAR. So conclusions: we created a modern and portable version of Samurai. We see a significant speed up you know, factor of 100. And again, a team with a diverse and complementary skills can have a profound impact on application performance. It's now possible to use the full resolution of the APAR instrument because, I mean, there was like, you know, the instrument can collect all this data, but then it would take a month to process it. And so maybe you wouldn't do that. And so that would be a shame because, you know, you have the instrument that is can collect that much data. Another bonus is that HPC resources are no longer needed for modest resolution configurations. You can run it on your laptop. And I think one of the cooler things, and I hope this happens, is that that Samurai can now be used in flight. So it could be mounted with the GPU on the plane, and you could perform your analysis, and you could adjust the science goals in real time as it's flying along. So the code's that fast now. Questions? All right. To compare the code performance between container, Docker, Charlie clouds, were you ever able to compare performance to a bare metal compile run? We kind of did. The problem was with the Docker and the Charlie cloud is that they would take you know, 2 days, 11 hours, something like this. And so you know, we would run it, and it was like, yeah, it still takes 11 hours. But I mean, there wasn't a kind of a really close comparison with that because we really kind of wanted to get it out of the container. I guess we could do that now that it runs a lot faster, and we could do that in an afternoon instead of a really long weekend. So let's go on to this next question. It's an impressive speed up with a CG solver. I assume that multi-grid would have done even better. Symmetric positive, definitely. Did we consider that? No, I don't know if we considered multi-grid. Allison Baker is really the expert on the solver stuff. I kind of let her, she does have a multi-grid background, so I kind of let her choose the solver for that. So no, I'm not aware if she did check that or not.